Ladies and gentlemen, I would like to introduce our first speaker of the afternoon, Robert Lubarsky from Florida Atlantic University, who will be speaking about elementary real analysis. Well, thank you very much for that very kind introduction. It's a pleasure to be here in front of you. You're probably all thinking that I'm going to tell you things like show you, for instance, why the derivative of x squared is 2x and stuff like that. That's because you're thinking that the title of my talk is this, whereas, where's the eraser? Actually, the title of my talk, thank you. You think this is the title of my talk, but actually, this is the title of my talk. I am going to be telling you a bit about analysis using the elementary real numbers. Let me say up front that my attitude toward this series of presentations is that this is supposed to be like work in progress, more informal kind of stuff here. So this is not a clean presentation. I don't have slides. I certainly don't have any results here. If more than anything, I just want to introduce this topic to you kind folks in the audience. So the general topic is, I think, as you could well imagine, we do have a notion of analysis and a real number. You must be familiar with the concept of a computable real number, and you can ask questions like, what can you do with the computable reals? Well, I've started to look a bit at the elementary real numbers. These are real numbers which are given by an elementary computation. The elementary functions are a small fragment of the computable functions. So let me try to give you some sense, without going into the full definition, of what an elementary function is. The elementary functions are, they're closed under exponentiation, for one. So it's not that small a category, not that small a collection. Like, this is already way more than the bounded arithmetic people do. So it's 2 to the x, 2 to the 2 to the x, 2 to the 2 to the 2 to the x. Those are all elementary. And it also ends up being closed under bounded primitive recursion. Meaning that if a function f is given by primitive recursion, but you have some bound as to the value for f, some elementary bound, then that would also be elementary. F given by primitive recursion, and it's also bounded by an elementary function. And other things too. There are a couple of other base functions that you throw in, closed under composition, this kind of stuff. So that's what the elementary functions are. There's all sorts of interesting stuff that you could do with the elementary functions. One of the more interesting things that comes out of this, which so far as I understand, and let me say up front, I'm ignorant of a lot of subjects that are connected to this. So if you know of anything related in a related field that seems similar to have some relation, please let me know about this at some appropriate moment. One of the nice things that you can do with this is you get the notion of an honest function. So f is honest if there are a couple of trivial conditions that we impose on it. It's got to be monotone. It's monotonically non-decreasing. We want it dominating at least 2 to the x. So monotone greater than or equal to 2 to the x. And most importantly, we want the graph to be elementary. So what does this mean? The graph is not a function. Okay, the graph is a relation. So what do we mean by a relation to be elementary? Well, we mean that its characteristic function is elementary. So for the graph of a function to be elementary means if I give you the input and a potential output, the potential value of the function, it's elementary to decide whether that's the right output or not. So you can have a function which is not elementary. Maybe it's growing way, way too fast to be elementary. But given the output, you can tell whether you have the correct output or not. You can't compute the output, but you can tell, given a number, whether it is the right output. You can tell that in an elementary way. That's an honest function. Now, this is something which is different from regular computability theory. Because, you see, if you could computably, and I mean Turing computably, tell whether f of x is y or not, then you can actually compute the value of y. You just search for it. You start with 0, start with 1, and you increment by 1 until the answer finally comes back yes. So this is not a distinction that you could make with regular computability theory, but it does come up in the context of elementary functions. So this opens up a different realm of investigation. One of the more interesting theorems here is that then, of course, what naturally comes after this is you want to relativize the notion of computability. You can talk about a function being elementary in another function. When you do this with Turing computability, you're speaking very much about information content. Rates of growth play typically no role here. I mean, if something grows too fast, then you know it's not computable. But in the case of honest functions, the whole thing can be reduced to just rates of growth. So you could so this they call the normal form theorem. Well, let me point out over here, this is work mostly of Lars Christensen, and some of the stuff has been worked on more recently by Andreas Weiermann and Jan Christoph Schlager-Puchter. The normal form theorem says that f is elementary in G if f and some list of arguments is, so this is what, if for some k, if you compose G k many times, so that's composition, and you apply it to the same inputs here, that this is supposed to be the bound for what's going on. And what we have is Kleene T predicate over here. So there's some computation for some k and e. There is some Turing computation. And so you find the least, if you can bound a code for if G provides you with an elementary bound, roughly, G iterated a certain number of times, can provide the bound for the closure point for this Turing computation, and then you use Kleene's U function to extract the result of that computation. There you go. So now that I wrote it down, this is saying that this property of being elementarily reducible to essentially comes down to being bounded by some finite iterate, some fixed finite iterate of the supposedly larger function. And then, of course, you have to recognize what's going on in some very computable way. So everything listed here is elementary. Finite composition, elementary functions are closed under composition. This bounded least number operator is okay. That you can do. Not the unbounded least number operator, but bounding is okay. Kleene's T predicate is elementary as a predicate. To extract a component from a number, so everything in here is elementary. The import of this theorem is this captures the notion of elementary reducibility.
But do you want to say if and only if rather than just if?
Yes. Thank you. So you can see that reducibility effectively comes down to a limitation on the rate of growth. Yeah?
But you don't have the direction from from left to right, right? So if f is just elementary in some dummy function, then you do not necessarily.
I'm sorry. Yeah, if f is in no, excuse me. G is supposed to be honest. So yeah, this is the point here. If G was just some dummy function, for instance, the constantly zero function, okay, that would be a counterexample. So G has to be honest, where basically the idea behind honesty is that whatever information it contains is already contained in its rate of growth. That is, if you were not to allow an honest function, then you could have a very complicated function that doesn't grow fast at all. It could be a 0, 1 valued function. It could contain a lot of information. So we want something that the amount of information that it contains is contained in the rate of growth. So that's the idea behind honesty. Okay, thank you for all of these corrections. To cover myself, I did say this was supposed to be an informal talk, a somewhat less formal talk. There you have it. So, yeah, and it follows as a corollary to this. Yeah, they call this the growth theorem. That for f and g honest, f is elementary reducible to g. I haven't introduced this notation, but you can guess. It's elementarily reducible to g if and only if for some k, f is bounded point-wise bounded by some iterate of g. So information theoretic reducibility really does come down to a matter of rate of growth. So, given all of this, we are very naturally set up to talk about degrees. Now, I'm not going to, but let me just mention in passing, you get a degree theory from this. You could mod out by the equivalence relation induced by this partial order, and then you get a notion of degrees. There's a bottom degree, 0, which is the, let's see, 2 to the x is an honest function. And that's the degree that's obviously the slowest growing, the smallest honest function. So the degree of the exponential function is the bottom degree, 0. There's this partial ordering induces a partial ordering on the degrees. There's a notion of jump that you can define. Interestingly, and I will mention this because I think it's interesting to see the way rates of growth play a role here. How would you define f jump at a number? If you compare this to the Turing jump, that's a very information theoretic notion here. What this is, oh, let me get it right. There's a +1 in one of two places. Let me make sure that, yeah, okay. That's what I thought. Yeah, so iterate f applied to x, x plus 1 many times. It's just a rate of growth notion of jump. This is enough, kind of like diagonalizing through all of the finite iterates of f. And this is a natural notion of a next larger degree above your starting degree. So you could talk about things like, you know, is this a lattice? It is. You can get meets and joins for this lattice, and just ask all sorts of questions about this order. It opens up all the questions you might want to ask about a degree ordering you can ask here. A certain amount of work has been done. We don't know an awful lot about this partial order. And there's certain basic easy theorems, but very quickly do we get to the point where we just don't know stuff anymore. So if I can convince any budding degree theorists out there who think that there's not a whole lot left in the Turing degrees to do anymore, or what is left is just too difficult, you may want to try your hand at this. I've heard it suggested, like Laura said one time, what's nice about this is the first step in what would be priority arguments you can replace by just rates of growth kind of stuff. You can avoid priority arguments. Or I think a little more precisely, you can just postpone the use of priority till a later step. That, you know, the first level you can deal with just by rates of growth. Not that anybody's made a priority argument here anyway. There's still lots to be done along these lines. What I did want to speak more about was the analysis part. So this is all the elementarity. Now let's talk about the real analysis. Just as there's a notion of a computable real, you could talk about an elementary computable real. Suppose you have a real number which is somehow given by an elementary function. What would be the right definition for this, and what can you do with these things? This is the kind of thing where I really, honestly, have not thought about this much. So some of what I'm about to say might end up being kind of dumb. This is entirely possible. If you could point this out to me, if you notice any such thing, if you could point it out to me quietly, I will be most thankful. Hopefully, there are at least some of what I'm about to say will have some actual interest behind it. The first question that I felt I had to deal with in this context is, what is a real number? What do we mean by a real number? So I've come up with a bunch of different possibilities. Let me list all the ones, or at least most of the ones I've come across. So I will say that a real number is strongly Dedekind. I'm not going to use the word elementary here, because everything I'm thinking of is elementary. So my general framework is I think of Dedekind, cuts, and Cauchy sequences. This is what most people think of for real numbers in some form or other. So I'll call it strongly Dedekind if for some elementary function f, r is the real number. For some elementary function f, if f of q is 0, then q is less than or equal to r, and if f of q is 1, then q is greater than or equal to r. So implicitly, q stands for a rational number. A rational number can be given as an integer. It's a pair of natural numbers. Well, a pair of integers, you do some sort of coding. It could be negative. You do some sort of coding of the rational numbers into the natural numbers, and so the elementary function applied to the natural number makes perfect sense. And it will tell you whether the thing is less than the real number in question or greater than it. Where I don't want to say if and only if, because in case the real number is a rational itself, then you have an arbitrary decision here. You can go one way or the other. So whether you can computably decide, given any rational number, whether it's a bit too small or a bit too big relative to the real number. I will say that it's membership Dedekind if, again, there is an elementary function f such that f of the pair pq, implicitly p and q are rational numbers and p is less than q. Want to feed it some honest interval. If this is 0, if and only if r is in the interval from p to q. If I hand the elementary function a rational interval, the function will tell me whether the real is in that interval or not. I don't have to say else the function is 1. Here, this one, I don't know if this is going to seem a little strange to you. I'll explain it after I write it down. Located Dedekind if either f of pq is going to be p, and p is in the lower part, or f of pq is q, and q is in the upper part. So given an interval, given some rational interval, we'll get some information about where r is relative to this. If r is down here, then it's going to have to give q. If r is up here, it's going to have to give p. If r is actually in that interval, it can give either one. So where does this come from? Where does this notion come from? Well, in constructive mathematics, this is the standard notion of a Dedekind cut. You have to worry about, in constructive math, what if the real number seems to be an endpoint, but you can't quite tell? You know, it could actually fall inside the interval, it could fall outside the interval. Your model hasn't decided yet how the real number r in question compares with the endpoint. So you can give up deciding whether the real is in the interval or outside of the interval. That's not going to happen. But in any case, in this case, you could tell, oh, well, this is definitely too small. Or if you couldn't distinguish the real r from the left endpoint p, then at least you could say, okay, well then q is larger than the real number. So this is a standard notion of a Dedekind cut from constructive mathematics, and it also seems to have an analog in this context. I will say that the real is Cauchy if the function f is a Cauchy sequence. I think this is the most straightforward version you can come up with, is a Cauchy sequence with limit r. You can actually have an elementary sequence with that limit and modulus of convergence. Two to the minus n. That is, with input n, you will be assured of being within 1 over 2 to the n of the actual value of the real number. Probably the particular modulus of convergence doesn't make much of a difference because it's elementary to go from n to 2 to the n to 2 to 2 to the n. But whether or not you have your hands on the modulus of convergence or not, that can be a different matter. If you're approaching the real so slowly that you can't get your hands on how far away you are, well, it's not very practical, and well, you could get into a lot of trouble if that's what you're doing. Although that would be another interesting notion to look at. Give an example of an elementary function which represents a Cauchy sequence but has no elementary modulus of convergence. You know, that's part of the cleaning up that you would want to do if you were going to do this. Now here's a notion which, you know, a lot of the stuff you could probably do with computability just as well as with elementary functions. But here's a notion which seems to be unique to this subject or undeveloped elsewhere. Talk about being honest Cauchy if instead of demanding that f be elementary, that it be honest elementary. If the f from above is honest, elementary. So to remind you what that is, it's not as though you input n and in an elementary fashion you get the output f of n, and that's going to be real close to the real number r, but rather f of n is some rational number that you can't compute, but you can recognize it when you get there. You can say, well, is 1/2 within an eighth of r? You get yes or no. Well, if it's no, then what about 15/16? And you can ask a more and more complicated question. And if you happen to ask the right one, the right value for f of n, then you'll get the right answer. Finally, I will say that the real number is interval Cauchy if there is some elementary function f which enumerates all intervals, all rational intervals containing the real number in question. This I got from looking at Weierhauch's book. There's a large theory about representations of various spaces, and this is what the notion of a representation in his style would come down to, an actual listing of all such intervals containing R. So these are literally a half dozen different notions of what an elementary real might be. I spent some time thinking about, well, which of these would be equivalent to which others and which would be stronger than some of the other definitions here. And I actually even wrote down which ones of these are equivalent to which others and which are stronger than each other. I'm not going to say it, though, because I don't believe what I wrote down anymore. So presumably these are not all distinct from each other. I'm sure there's some pretty easy arguments that you could give to show that if you can make some of these decisions, then that would give you certain others over here that you could make. I'll close by raising a question that Andreas Weiermann asked me about this, because there are all sorts of things that you would want to do. First of all, do the elementary reals form a field? Obviously, are they closed under addition, for instance? This isn't completely obvious. Even this one over here, I don't know if it's closed under addition. Suppose that you have two elementary reals, and it's, one is the negative of the other. So if you add them together, you get 0. Okay, well, 0 is certainly elementary, but what if you can't quite tell which one is bigger than the other? So, in absolute value, they might be off a little bit, but maybe you just don't know. So I don't think this is uniform, because there's certainly no way of telling uniformly whether one real is bigger than another. So there are all sorts of surprises that could be coming up. If you want to talk about whether it's a field, then if something's not 0, you want to be able to invert it. But we know that if something is close to 0, it can be hard to get an approximation to 1 over that number. You would need to bound something away from 0 if you want to show that it's multiplicatively invertible. So there could be problems there. But I think the interesting question that Andreas Weiermann asked me for any of these notions of reals number is the corresponding set of reals real closed? This is where things start to get into gear. That is, given a polynomial with coefficients that have any of these characteristics over here, is that enough information for you to get your hands on any particular root of that polynomial? And I've spent some time thinking about this. This is certainly known territory here, the fundamental theorem of algebra, and trying to approximate roots of polynomials and this kind of stuff. There's stuff known about it. But when you bring these size of computational sorts of considerations into it in any of a number of different ways, well, who knows quite what's going to happen. And that, my friends, is the state of affairs. Thank you.
Any questions?
Please.
I'd like to go back to the honest functions. I'm curious about them.
Mhm.
Is there a literature on them?
A small literature, yes.
I mean, every honest function is computable.
Oh, yeah, sure. Because your graph is elementary, yes.
Is every computable function bounded by an honest function?
Well, yeah, I would say so because Kleeni's T predicate is elementary as a predicate. So yeah, I mean this itself, that would give it to you right there.
So in proof theory, there are the hierarchies of the computable functions with nice versions, which presumably are all honest.
Well, for what it's worth, we only have the notion of a total honest function. So you could use this to get a fast-growing honest function. You can only bound total functions this way. But yeah, it's a fair question that, yeah, the rates of growth of the honest functions go throughout all the computable functions. Mm-hmm.
More questions?
Well, even if, let me say, are any of these equivalences here sort of obvious, or any of the questions obviously stupid? Good, okay, so if it's not that obvious, then I'm satisfied. Even if they do turn out to be trivial, it won't be so bad.
And thank you again.
Thank you.